Hi, welcome back. So on this tutorial I'm going to show how to install and run with different configuration the example for run the different work for the class for the medical physics class at the University of Edinburgh. So let's start like from you should receive an email already with a link to this software repository. I put this code on GitHub. It's just for personal choice. I know people need to use it. You just mostly the only thing to use it is just for download the code on your cloud machine or on your local machine if you have a Jump 4 installation there. So the way to simple to do it is just please go to the link provided in under this video, and it's on github.com Lorenzo Zana EdMedPhysics. So just you go there and you must gonna click here, the left click on the mouse on clone or download. So you're gonna click on this. It's gonna open a menu very much there is a link there to this one there, and what we want to do it is copy to the clipboard there. So we're gonna go there and click on that. That's gonna save it on our clipboard on our computer, and so from this we're just gonna go back on Cloud9 and go there. So just for simplicity, just start create a new terminal here. So so back here in our workspace, so we have a clean terminal there, and what we need to do is download locally this software. In order to do this, we're going to clone the software. Don't worry about if you don't write down the commands. I'm going to write down these commands under the video, so you can just go through it later. In order to see better this video, just increase the resolution to high def. The resolution should be fine. So we're going to do a clone it. So we do a click clone, and then you're going to copy. So since it's in the clipboard, we're just going to do Ctrl V, or whatever you use. If it's a Mac, it's Command V. Okay, there is the link on github.com or Zana and EdMedPhysics.git, and we press enter, and this is gonna clone locally the code as it was written there online. I'm gonna look here, okay, here, so you can see where is the mouse there. There's the EdMedPhysics there. So we're gonna change the directory, so CD to the EdMedPhysics. Okay, we are there. You can see there the structure of the code. We can look at the structure of the code, or we can just go here, browse it on the left. Copy there. So we can see there is like a part of the code. I mostly say how the code is running. It's here, but the main part of the code of the structure is going to be inside. So headers, mostly of the structure of the things. Mostly, for example, we can open this one. We just go there on the menu and double click on it. Because mostly that our mostly Jump 4 is written in C++, and every code is going to use this one. There's a strong use of virtual classes, so there is some standard way to run it, and that can be overwritten by the user to this. So on this one, we're going to initiate some virtual classes. You can see then, for example, they're implemented there in the source code. So we're going to open the source there, and this was metaphysics.ld.h, and you can see here this is going to be included here on the top together with other things. For example, this one is important because that's the way we're gonna I fill the histogram, I fill the data file on this one, and it's done here at this macro where I process the heat and must calculate each step all the information I needed. Oh no, going through the code is not needed. It's if you want to do something more and change the way it is running, change the box size of this, you probably want to need to change also the way they fill the histogram and so on. And for example, here there is our example. It's a box with the length of 50 centimeter and with the size of 30 centimeters. So Jump 4 use the coordinate from the center of the box. So for this reason, the z coordinate is going to go from -25 to 25, because it's a 50 centimeter in length in Z. So that's the reason for just for simplicity to put it at 0. I just shift it for 25 centimeter. It's done here at this line of the code. Every time I fill the histogram, or my fill the on top of there with the Z position. For X and Y, I still prefer to I put it mostly where the beam is coming at 0, so we can see moving left to right. We can see the symmetry on there, so I just kept it there without shifting. Again, this is not needed for the code, but again, if you want to modify something in the code, that's what you need to touch. If you want to add on the technical construction, the place you will not go will be on the technical construction here. On the left there, we can scroll down and mostly see that we have 500 small layers of 0.1 centimeter, so 1 millimeter in thickness. Of this one, they are made of G4 water, and mostly G4 water. So that's our box this. So we say mostly 500 at 0.1. We have our 50 centimeter in length and 30 centimeter this one. This is mostly has been done in order to kind of control the step size, to be sure that everything was deposited at a certain line, to have like a nice progression and a mostly a resolution roughly 1 millimeter in our histogram. That's more than enough for our studies. So the only want to do this, we don't want to step, this is decided by the step in the GM4. We don't want to push the step to become too small, because each step it will be randomly selected between the maximum step and 0, and it's going to be calculating the full interaction with cross section. So more step we're doing for a particle to energy deposit, more time it's going to take for running our simulation. So we can push it over a certain amount, but pushing more, we don't require that much information, we're just going to lose in computation time. So 1 millimeter resolution is a good enough resolution for this project. That's the reason we decided that this step can also be defined in different ways. I know, just this was some easier on this example. But so this is mostly how we structure the codes. Now let's go back and see how to compile the code, how to run it, and so on. So we're back here. Remember we are inside the EdMedPhysics directory. You can look at there. We are on workspace EdMedPhysics. And now we need to change directory to this directory. Now we look inside this directory. There is a cmake.txt file, and that's where we're going to point it to our cmake. So cmake is used now in because it's kind of like add portability to the software. People don't need to run their own compilation program. They need to work in many different configurations. That's I know it's a lot of computational issues, and for maintaining like require normally a lot of time. Most of the time was due to maintaining this one to work on different configurations, so on. So this one use cmake. That's kind of more portable, and let's see how it's working. So we want to compile, and it's going to work if you don't do this. You need to make a directory. It needs to be outside the source of the code. So inside this source of the code, we are going to make a directory. So it's going to build it, and we're going to call this directory build. So we make a directory. Again, just all these commands are going to be written under the video. Don't worry too much about this. Just copy and paste what in a sequence, and it's going to be fine. So we're going to make a directory, and we're going to change directory to this build directory. And now we're going to point cmake to where the cmake file is. So we're going to type cmake, and we're going to go down one directory, but the cmake list is there. So we point to the directory where the cmake list that we want to use for this code inside. So we point to this one and just type enter. This is going to look for all the source code and create this make file here that with all the different configuration, like and so on. So after cmake, we just need to compile the code. Then mostly is gonna what the compiler is gonna do. We're finally be able to create executable. This is gonna link all the GR4 library to the way they're gonna run on this example. So let's type make here. Again, we are still in the build directory, and we're gonna wait a little, and it's gonna compile this code on this one. So while we're at it, so now we see that we have created this build directory, and the code is being compiled, so on. Let's go through some of these different options here. So for example, let's open this run3.mak. We just double click on it, and it's going to open it on another tab here. So this is a simple way this is going to be running. This one is also the possibility to be run in parallel and so on, but it's not needed here since we don't have that much CPU power here, and no point to run in parallel. This, if you run it local, could be you need to run it in parallel, but for this example, it's not needed. It's just over pushing the system. If you want to compile in parallel, you need to compile jump4 in parallel and so on. So here it's not needed, so on. So just go through the macro. So mostly with when you started with the hashtag, this file line is not going to be read. And then add this command just written by simple like what is the command here, and then command lines. For example, here that's two main command that you're gonna modify. Here it's there's a gun particle, so mostly jump4 is shooting like a particle. They're defined as a gun, and the type of particle is defined here. In this case, is a proton. Then we can change also the energy of the particle. It's in the case 100 MeV proton. And in this line here, we decide that in progress mostly is going to be outputting on the screen every 100 events. Some after the screen is inside the code is mostly saying how much that event has been, the energy has been deposited, just to have go through that mostly the code is running correctly and so on at each step. So on, something that is expected there. Mostly if you run a high statistic, you want to see that your code is running correctly. And in this case, mostly we're gonna run 1,000 events. So we're gonna, our gun is a proton, it's gonna run 100 maybe proton 1,000 times. And this is the example is gonna be running this macro. So let's go back here. The compilation of the code has been finished, and we can look here because we see here on the front the link executable at the EdMedPhysics executable, and then we look here in the code, see the executable is on green. So in order to run this macro, we need to run the executable, and again with a different option there. Let's just simply run the run3.mak, that's the one we just visualized before. And the way we want to run it is mostly we say where is the executable, that's here. So in order to say to the computer that it's here, we need to type dot dash and then EdMed executable. We forgot how to run it because it's a while we don't run it. I forgot what it is, what to say on this one. Okay, the command will be under, but again I don't want to look at the video there again through it and so on, and so I'm just going to type -h, that stands for help, and it's going to tell you mostly how to run it. So we're going to run a macro. That's the main part we're going to get away, so we're going to run again our executable. So we'll type -n in the name of the macro. So our name of the macro that we run around is say was run3.mak. That's the one we used before. Again, it's going to run 1,000 proton of 100 MeV over a cube of water with size 50 centimeter in thickness and 30 centimeter in width. So let's see how fast it's going to run. Should run pretty fast. So you can see some out on the screen. You can read through it. It's mostly going to tell you what kind of cross-section it's going to use during this simulation. It's already finished, as you can see here. You can see at the end there's mostly a root file that's been created. The root file is going to be our file. There's all the information there. So we can look at there at the top of the screen, and mostly we'll see what's the length, average length of the target. So we can see here mostly this one deposit. Mostly you have just a lot shorter track there, but mostly was around 7.8, 7.9, 7.7, so on. So we can have some idea where is the maximum of our energy deposit. It seems like there is some more stronger peak around 7.8, 7.9, and so on. Let's look inside the data. So there are different ways that we can do this. One is simple way, just mostly analyze directly, look inside this root file. I put some simple histogram inside, together with a tree that's mostly have the recording of the data deposit at each step of the particle where it's going to be depositing energy. So for just an example, let's go inside there and let's go looking at this. So here's the root file there that's been just created, so we can, in order to visualize it, we cannot visualize it directly in root on this one. So what we need to do, we can just download it locally. So we're gonna click on download, and then we go back here on the first tab on the left. If you don't see this one, just mostly click load or reload the page. So this is gonna load this JavaScript implementation in order to run root. That's mostly analyze the root file, and we want to load the root file. We just download it to our local machine. So we're just gonna monitor this tab sometimes, and depending on the screen you're using, this option here, the select file, local file for reading, it's not seen. You can see different example here. For example, that what you can do, how much you can visualize on this root, but that's not the point of this example. So let's load our root file here. Okay, I already have something like that tested before this morning on this. And okay, let's just open this proton file. We just open now. That's the latest file here. Okay, it's already been open here on this one. Let's look at the profile. So we are expecting what isn't there from the text file, something around 7.8, 7.9 of this one of the distribution. So let's go back to the first tab, and mostly I put energy deposit versus Z. We can look at this one, and you can see here mostly our energy deposit there is around this area there. We can zoom in on the plot, just mostly select with the left mouse on this one the area, drag it through it, and you can select the area there, and you can see mostly that we're planning there on 7.8. If you want to draw it like slightly in a different way, just right click on the, select one of the points, and you right click on it, and then draw with, and select histogram. It's going to be slightly different. You can select in different ways. The one before mostly selected with the arrow at each point there. So we can see here that our again our peak was around 7.8 and 7.7 and so on. That's what we expect also from simple article we saw on 10 times on the screen. Over 1,000 events was recorded every 100. Again, the 7.8 centimeter here, the z-axis is in millimeters, so we have 78 here. And so we can see if you want to go back, or like how I want to go see again what it was before, because you like select again the axis and here and go and so on. And again, so about this one, if you're part of a lecture, you're probably already familiar with this. This is exactly of Bragg's peak, where we have mostly our energy deposit is mostly maximized at a certain point in length, and mostly with our proton beam doesn't have so much energy deposit after. So this is a zoom of 10 centimeter. We can also see, I don't know, 20 centimeter there. Again, it could be when I plot in a way you can see it slightly better. So we can see here there's mostly no energy deposited there after 80 millimeters from the surface. So we can see why proton therapy becomes so important. When we want to deposit all the energy is mainly deposited in a small area here, and then nothing goes much go through. There's not that much energy deposited after. So the Bragg's peak is really important to define this edge on the spectrum, and defining this one in a patient is like one of the challenges of medical physics. But again, if you don't want to like too much radiated after, that could be a good choice, and that's the reason could be people start to study like use of proton in for irradiating tumors and so on. Okay, so that was a simple way to analyze it. The other way that we can analyze it on this one, so again, here we have energy deposited versus Z. So mostly at Z we integrated the full energy deposit in that energy band. So we can see what the size of the bin there. So mostly go from 70 to 72 millimeters, and then we have 4014 entries, and then and so on. So another thing I recorded here was the length. So this is slightly different. So what we plot here is let me let's plot in this way. You can clearly see it better. So we can clearly see again there is a peak here of roughly the same distance we had before, and then so what we have here is mostly the average length of a track that is going to go through the material that is now its water. So we saw before that we have energy deposited of mainly picked at 7.8 millimeters, and now we see mostly all the track they have a length of 7.8 millimeters. So what we come out with it is mostly we can see our proton is slowly losing energy. It's traveling average to the full length to the 7.8 millimeter, and the maximum energy is going to lose is mostly at the end of his life when the energy is going to be low. That is going to dump mostly all his energy out, and so on. That's the reason of the Bragg's peak, and that's something important result just for simply analyzing this histogram. So another thing that was recorded here is again our full data structure. Since you want to do could be some cut almost analysis. Here is full integrated in X and Y, Z, and so on. What about you want to check something more? So here again there are two options. This one they're directly here through the tree, through this Java part here. We can just go right click on the I'm going to right click on the tree, go to draw, and click on the player, and again here it must show you like what kind of expression there. So let's see what's the structure of this tree. So we're going to left click on it, and we see what is recorded there. So energy absorbed in X, Y, Z position. So the example one you want to see is we can plot X, Y, Z. So we probably want to put our beam going through the z-axis horizontally. So we're going to put the column X, Y, and we're just going to draw it. So we should be able to see our horizontal beam line is going to go through that. Okay, currently here is our horizontal beam line, where in the x-axis here is our z position, and the y-axis our x, and so on. Here, so we can see mostly that our beam is at 0, and so on. There. And over here we just see a lot of points. Could be we want to see a little better there. So there are different options there. So mostly we can right click on the. Could be we don't know the option. We just right click on the histogram. Going to be selecting at one point, and I'm going to see draw with. For example, we can select GLI box 1. That's not a color. Or could be we can do something different. No, box 2, for example. Okay, so this one we're gonna see just how many times the energy has been deposited there. And we can see mostly our beam spreading out in X and Y. Sorry, Y and X. So we're gonna lose some focusing on the beam. But in order to do this, we kind of want to analyze it a little better. So let's see how the focus of the beam at different places. For example, let's look for Z position less than 10, in case here is this x-axis in here. But so we want to apply a cut, and again we plotted this one as a box 2, so that's the option here. So we're going to apply the box 2, and so we want to put a cut. And look, how does it look if for Z less than let's see 10? And what we want to do is to look. We're not going to too much care about the Z here because that's already there. We're going to cut it. We're just going to look at X, Y position. So in order to do this, I just draw it again. You can see this one like this. That's just going to be the plot there. You can see it's kind of focused there. You can't see that much well. So let's just plot in a different way. So col Z is should be drawing here. See, there is also a scale here on the left. So mostly we see our it's a color scale mostly of this plot. That mostly show like on the yellow it's the red one on 1000, and on the blue is mostly there's nothing there. So our beam is really focused at 0, 0. You can see here. And let's see how does it go when we go close to the end. So the dimension was going around 7.9 at the end. Again, it's millimeters. So let's go around after 70. What the profile is gonna look. So, but in the same way, we can see the profile got a lot more spread out. We don't have that many bands, so we don't have that much of a distribution. Again, our beam profile is a lot more spread, and so that's we can see mostly the focus of the beam got worst. And what I know this is exactly what you can do, but I know making something like a Brax peak require a little more in-depth analysis. So if you're not just fine with the simple plots created here on the left, the one we saw before here, you want to do something. Analyze directly this tree file here. Again, this one, parenthesis 1, is the one in your local machine. It's been loaded here. What you have there is something in the cloud. And so if you look here, and let's start the root, we see this EdMedPhysics, the root doesn't have that one, because that's the one in the local machine file, in the cloud machine. So this file is going to be rewritten every time you run a different simulation. And so just if you want to keep it, you can change it, you can copy it. This one we want to copy to something that's we're going to copy to something that makes sense, that we have been able to understand. So it's proton 100 MeV dot root. So we understand what it is. So we can copy CP or move. Just copy like this. Alright. So what about if you want to run a more in-depth analysis? I wrote a simple analysis code inside here. So let's just go through it. It's called inside directory build. It's been copied there. And let's just go through it now. Just double click on it and just read the file mostly. So here is made directly to read this EdMedPhysics root file. It's going to read the tree here. It's going to set up some variables. Then they're going to be linked through the variables inside the tree there or the data files. So now my code understands that when I'm going to read it, that this variable corresponds to the one inside the tree that we was visualizing before. Yeah, this step here on the drawing there. So again, all this code is well commented there, so you can just read through the whole comment. And so let's just go read through it here. So we're gonna get the total number of entries here. Again, we have 1,000. We run 1,000 proton. We expect to have 1,000 entries. No, because each entry is recorded at each time the proton was losing energy. So the same proton can lose multiple times its energy. That's what we saw before. Our node is gonna just be recording at 8 centimeter roughly. So in fact, if we check our tree here, when we're going to analyze this one, you can see, for example, our X profile here, that is 161,692 entries. So it means one proton in average loses energy 161 times in our code in the 8 centimeter radius range. So we get our full number of entries. Then again it will be our 161,000, but the code gets it automatically. Then we're going to create some histogram. We're going to plot this one. We're going to be exactly the same thing that we saw before. Just this time we're going to create it where we can play a little here and so on. So this will be the name of the histogram. It's also defined as a name here. So this is kind of need to be single be decided, so each histogram will have a different name. You can see it's different, slightly different name. This will be the title written at the top of the histogram. A semicolon is going to divide it for the x-axis, the first is on semicolon, and on the y-axis after the second semicolon. This will be the number going to be there, and again it will be between 0 and 50 because that's where we have our material. And this one here is going to be another one with the same structure. And this time it's going to be just something different on the y-axis with just number of events. I'm going to go through later when I'm going to fill the histogram. And here we're going to play the same one. We're going to apply a cut. We're going to show you how to apply a cut. Where, for example, we are going to put a cylinder of 1 millimeter in x squared plus y squared. So we're going to put this small square of 1 millimeter. So let's go through the code here. So we're going to loop through the whole entries from 0 to the total number of entries. And so we're going to get the entry there. So when we get this entry, each event written in the data structure, there will be a collection of EABs X, Y, and Z. It's going to be linked to the variable inside this code. So we can actually read it now. And we can actually use it to fill our histogram. So that's what we're doing like the next step here. We fill our Z. This is simple. We fill like the Z coordinate there. So we're going to see where there will be an energy deposit different than 0, bigger than 0 inside the water. But in order to get the Bragg's peak, we're going to see how much energy deposit been done at each point. So in this way, we kind of need to weight it. So mostly in this case, each event is going to be counted as 1 in the first case. Written end on this one, written end to be counted at 1 is going to be putting the energy absorbed at that point. And again, just a reminder, here is written in millimeter, the Z coordinate is in millimeters, so if you want to transfer a centimeter, we need to divide it by 20, since this is our range. We write here, you want to write in centimeter. And again, if you want to apply a cut, you can see a small if clause here, compressed by parentheses, and put our cut here. That was, we wrote exactly the same thing here. And there, and we're going to fill the Z. We're going to see mostly how will be the progress. The number of events is going to be going inside this small cone, and mostly we're going to see our defocusing. So we expect our number of events decreasing as a function of Z. And when we have filled this histogram, again here there's the end of the loop. There, there's going to start it here at on the entries here. We're going to put through all the entries, and now the loop through all the entries is finished. And what we want to do, we want to plot it. So we're going to draw, we have different ways to draw it and save it and so on. For example, we could save some simple picture. In case we create a canvas. That's mostly a place where we want to draw it, and we're going to simply slide type draw on this one. Let's see how it's going to draw on this. And we're going to save this one from the canvas. We're going to save it as a JPEG, simply because it's easier to visualize it directly from the cloud. And we're going to do the exact same thing. We got the 3 different histogram there, 1, 2, 3. And what we can do also, we can also like compare it. So we can draw it on the same plot. In order to do this, we don't know which one is which and so on. For example, yeah, we're going to change the color on the sample Z to 2. They're mostly saying change it to red. And again, we're going to change the title to this. And see, now we don't have no more, we'll have something between energy deposit and end. We don't know that much on the y-axis after this one. Y after the semicolon is left empty. And we say number of events, that's the one, it does the split in red. The author is being kept in black, that's the default. So first it's going to be drawing histogram, and the way we draw it in the same histogram, we just type same on this one. I'm going to show you can do the same thing on the root file, finally we're going to get at the end. And we're going to save this one again as a JPEG. Not a way that we can visualize this output that we have from our simple analysis. We can save it as again in a root file. We can again visualize it again with the Java root thing that we showed before. We define our final output as guess what is an ASCII output of root, and we're going to write each single histogram, and we're going to close the output file and so on. This one mostly is going to tell me, mostly is going to recreate the file at each time, and we're going to write this one. So again, file is going to be overwritten, and you need to be just keep your analysis there. Again, call it proton analysis 10-100 maybe the root, so you know which one it is in this case. Let's just run this simple macro, and again this one is running on EdMedPhysics the root. That's the one we just created before and just copy there, but you can see here EdMedPhysics, the root is still there. So we're going to run our analysis. So running to this, we need to run in batch mode because we don't want to have some graphing interface directly on this. It's actually not going to run faster like this. So you can see how fast it's going to loop through 161,000 events. So we type a root in the analysis code installed directly in this cloud machine, and -b, and the name of the marker that we run just saw before, analysis example.c. Run through this. Okay, the marker is already finished. If you want to do something else with the file, it's still your prompt here. You can do something more. You can just keep on doing what you write in here. If you want to do something else, like we can draw again here. So, example. All these are still in the thing, so I don't know. Yeah. Okay. So it's the example. The again, it's a pointer because there was a pointer there. Just so let's keep on going. What we're doing. If you want to save a little more file there, and there, so it's still saving to our canvas there, so we can save it again and print. Example dot I know you can save it, for example, now as a text as an option there, of PNG or PDF. PDF you can visualize it directly to the cloud. That just some picture format. That's this one. Alright. So we have our example G. That was the same as this, and should be exactly the same as this one. And if we double click on this one on the left, we can directly visualize this one. We can see again our Brax peak, and there we can modify the range in order to visualize better the Brax peak and so on. And we could do a comparison where we plot both together there. They can plot. The scale is decided by the red one. That's the black one is a little over. You can modify the scale a little if you want. And again, picture cut here. Remember, we put a cut on the in a small cone x squared plus y squared less than 1. You can see as we expect because our beam is broadening. Also, if the amount of energy deployed as a function of z was kind of flat, it was kind of flat. Actually, it was peaking at the end there. But you can see mostly when we look at smaller curves since our broadening, you can see there is a lot less of that in the same cone there. So that's need to be think about it when there will be also some broadening in XY depending on the beam you're using. Somebody will have a better profile in Z, but could be in XY there will be more different. So that's something to keep in mind when you do this analysis on this one. So again, as I mentioned before, we save this one also in a root file, and to visualize it directly into JSS root, we just again load it locally, and we're gonna go through the tab there and open it. And it's up there, and okay, that's the same system we saw before, and you can just mostly copy there, same as before. And I can mostly grab there on this one. Different option on drawing, and so we draw with error. Okay, we have a resolution with the error, that's not that big. So that's mostly saving the same mistake in a root file that you like do some post-processing on that and so on. Okay, let's go back now to the different macro. Let's just close down the tabs here since I start to have too many open. Okay, so there are different macro here. So just some more points. So some of the part of your test is going to show like how to maximize your profile over, for example, a 10 millimeter depth. So how you want to do this? You want to probably be running like a different kind of configuration with different with the same particle with slightly different energies. It's going to go to different depth, and could be you want to see, could be some of the project also was showing like how to apply a magnetic field there. Let's just go through this. So are we going to run multiple particle, multiple this one here? Here mostly we can run it consecutively, and we can put it in our macro. We can decide our particle can be actually the same all the time. We can just modify the energy and decide for a certain energy how much statistics we want to run. Remember, you want to try and focus on a certain point. So it could be we can decide a certain profile over a certain day. Remember, we need to do integrated those over certain range in z, x, y. So we can have like different properties at each time. So if you don't write any particle, by default it's going to write 50 MeV electron. That's the default setting. So if you select any energy and particle, that's what is going to be running. And there are different particles you can run. As you can see here, we have electron. I mentioned before proton. Here we have a mu plus. I think one example is also mu minus. The thing you need to run. Protons I showed before. I know you can do much more fancy stuff when you can, for example, remove the Brainstorm effect inside there and see what is just given by certain process, the energy deposited by certain process. Again, we want to put sometimes a magnetic field. How is with this magnetic field? There's an example here, run1.mac. It shows an example how to run a part with a certain magnetic field. We're going to put a global magnetic field. It's going to mostly be a magnetic field inside the full volume of a certain value. So what is set here is mostly global field set value. It's going to set Bx in case 0.2, By 0, Bz 0, and the unit, this Tesla. So this one, the magnetic field here is a 0.2 Tesla applied to it. So that's keep in mind if you want to run some of the example of this one with some magnetic field. That's how you need to run it. There are different parts you want to run. I'm going to write at the bottom of this video all the different particles that you need to run for the different testing. And yes, so I think that concludes my macro. So we have different options here, for example, pi 0 for just simply modifying the macro. So one of the options I think was pi minus. We can see all the particle code is going to be written there, and energy is kind of self-explanatory there. And so again, thank you for your attention, and then if you have some questions, just drop me an email. And just could be drop on my office. I'm on the 8th floor. You can find my office easy, or could be ask Michael or Dan by email.